Hi, welcome again to this multi-part series in which we'll be tackling a couple of past papers in the chemistry section of physical sciences. My name is Pulka and I will be taking you through today's session. We are going to be carrying on with the November 2017 DBE past paper. And in the previous video, we had looked at all the multiple choice questions. Now we're going to be going on to question 2. Like I said, question 3 as well. And if we have enough time, question 4. Question 2 is the organic chemistry section being tested over here. And, let's dive straight into it. So question 2.1, they say, study the structural formula below. Okay, 2C's on the left hand side, 1, 2, 3, 4C's on the right hand side, connected by an oxygen as well as a double bond oxygen. So this is an ester, and specifically because of these two carbons over here, we are looking at ethyl butanoate. Okay? Ethyl butanoate is the name of our ester. Just write it down here. We are looking at ethyl butanoate. And a fun fact about esters in general, it is the only one homologous series group which name will have a space in between the letters or the parts of the word. Normally, the rule is that you will have no spaces in the word. You will have dashes between numbers and letters, and you will have commas between different sets of numbers. So yeah, ethyl butanoate, and let's have a look at what they want us to answer. So they say for this compound, write down the homologous series to which it belongs. Like I said, this is an ester, right? Let's just move that quickly. Now will be the answer for 2.1.1. Then the IUPAC name, might as well just pull this down now. Once it starts behaving. Nope, not going to behave. Let's pull it the other way. Okay, IUPAC name over there. And it is an ester. Cool. The IUPAC of the organic acid used in its preparation. Now, an ester is made through the reaction of two different homologous series groups, namely the alcohol as well as the carboxylic acid, right? The alcohol will give you the ethyl part, and the carboxylic acid will give you the OH part of the ester. So in this case, we're looking at this specific part because they're asking for the acid. And so therefore, we are looking at butanoic acid. Let's see if we can fit it in here. Butanoic acid. There we go. Fits perfectly. Okay. Then the structural formula of its straight chain unbranched functional isomer. Okay. So when it comes to functional isomers, we are specifically looking at either aldehydes and ketones, which is the first type of functional isomer pairs, or we're looking at a carboxylic slash ester, which is the other type of functional isomer that you can get. Now, in this case, the functional isomer for this ester will be a carboxylic acid. And specifically, if you look at the number of carbons, 1, 2, 3, 4, 5, 6, you would be looking at hexanoic acid. Let's just write the name over here. Okay, we are looking at hexanoic acid. Now, in me writing down the name, that is not the structural formula that we're about to do just now. but just so that we know exactly what we're writing the structural formula for, let's just put the name down there. Okay. And it's not the condensed structural formula, it's the full-on structural formula for um, for hexanoic acid. Okay, let's just draw it quickly. So you'll have a C, well, you'll have 6 C's, 6 carbons, all bonded to one another, 5 and 6. Okay, and branched off to that will be a oxygen as well as a double bond oxygen to show that it's a carboxylic acid. Okay, just write that down properly. Okay, cool. Then all that's left to do now is to add all the hydrogens, right? Let's give ourselves a bit of space. And if you look over here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So over here, we're meant to have 12 hydrogens as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the 12th one will be bonded to this oxygen over here. And there we go. The rest of them are all hydrogens. I will save the time of going and adding H's at the ends of all of these stems, but they are going to be hydrogens bonded to each of these stems. So yeah, that is basically the functional isomer for this ethyl butanoate that we have, and its name is hexanoic acid. Right, now they say write down the structural formula for 4-methyl pentan 2-1, pentan 2-one. Sorry, read that wrong. Okay, no problem. It will, first of all, let's just dissect the word that they have here. Okay, at the end, they have own, so we're looking at a ketone. Then, after that, the other thing to note is the fact that there is a methyl bonded to it in position 4. And the last thing to note is the fact that it's a pentan 2-one, meaning we have a methyl branch or a singular carbon chain branch bonded in position 4. It is a 5-parent chain carbon bonded ketone, hence pent for 5, and the oxygen double bond will be in position 2. Okay, so let's go about drawing this quickly. And again, let's give ourselves a bit of space. We're looking at, like I said, 5 carbons, 2, 3, 4, 5. And in position 4, let's make this position 4. Okay, so we'll be counting from right to left. In position 4, we'll have a singular branch, right, with hydrogens all over the show. And in position 2, we will have our double oxygen bond. There we go. The rest of these are all hydrogen bonds. Okay, hydrogens again at all the ends of the stems. We'll save the time to not go and draw them, but it is implied that they are all hydrogen stems. Okay, 2.3. They say, well, consider the structural formula below. Well, first things first, I go on and I notice that there is a triple bond, so this is an alkyne. Okay, it is if you try to see what the parent carbon chain would be. Let's have a look. 1, 2, 3, 4, 5, 6, 7. Might not be necessarily the longest chain that you can get. Let's have a look. 1, 2, 3, 4, 5, 6, 7. 7 over there as well. 1, 2, 3, 4, 5, 6, 7. That way as well. Well, it seems as if this is definitely a 7 um, a 7 carbon link alkyne. So we're definitely looking at heptine. Okay. Um, for argument's sake, let's just choose it to be that. Okay. That's our parent carbon chain. Cool. Then from that, we will have a couple of branches. Now, the first branch is that one. In position 2, you have a branch in potentially position um, 3, which is an ethyl branch, and you potentially have another branch in what could be position 6. What will govern that? Well, we have to look at what our position number for this triple bond could be, where it will be its smallest. So in the direction that I had previously assumed, this would be in position 1, 2, 3, 4. If you look at it the other way around, position 1, 2, 3, and there we go. So it is easier for us to look at this going in that direction um, than it would be going in the left-right direction. So this would be position 1, position 2, 3, and so on and so forth. Okay, cool. Now looking at that, this then would be in position 2. Okay, we will have a methyl in position 2. We'll have an ethyl in position 5, and we will have a methyl again in position 6. Okay, let's go about naming this now. Okay, and given the fact that ethyl starts with an E and methyl starts with, well, in this case, we'll be looking at a dimethyl. Um, Regardless, um, methyl starts with a M, and so therefore the E will take preference. And when we name this, remembering the fact that it is not an ester, and so therefore there will be no spaces between each letters or each part of the word, but rather we will have hyphens between the numbers and letters, and we will have commas between the numbers themselves. Let's go about naming this, and we are looking at 5 dash ethyl, then dash, because we're about to put another number. We will have a methyl in position 2, we will have a methyl in position 6, and dash, and because there are 2 of them, we're going to say dimethyl. And remember, again, no dash, no commas if it's still words, but because we need to consider the fact that we have a triple bond in position 3, we will say dash. Okay, go back to what I was doing. We will say dash 3 to show the position in which the triple bond is, and this is heptine. And there we have named it, which so happens to be the answer for 2.3.2. Now, the answer for 2.3.1 is it is an alkyne. Yeah, triple bond, alkyne. And it seems there we are. We are now complete with question 2. Oh, my bad. My apologies. They did not ask for the general series it falls under, but rather the general formula for that series. So in actual fact, what we're looking at is C, N, and H, and 2N minus 2 would be the general formula for an alkyne. There we are. Okay. And now we are officially done with question 2, it seems. Let's tackle question 3 now. And question 3 is where they bring in chemical bonding into the idea of organic chemistry. And basically, they say the vapor pressure versus temperature graph was obtained for 4 straight chain alkanes, okay, without any branches. No problem. From P to S, each compound differs by a CH2 group, meaning every time we go to the next one from P to S, so the difference between P and Q is they've added an extra part to our parent chain. So for example, if we started with a methyl, the next one would be an ethyl, third one would be a propyl, a propane, and so on and so forth. So they're just adding more carbons to work with. Okay, cool. Let's dive right in once again. And 3.1, give a reason why alkanes are said to be saturated. Very simple. The difference between saturated and unsaturated compounds is saturated compounds only, well, the carbons only have singular bonds. Okay, so we're allowed to have saturated compounds that have double oxygen bonds and so on and so forth, but the carbons can only have singular bonds, right? Then question number 2. Question number 2 is define vapor pressure. Now, if I remember this from back in my day, this is the temperature at which is the temperature at which, oh, sorry, my bad. Not boiling point. That was me about to define boiling point. The pressure, sorry, at which the vapor exerts the pressure, not at which, but let's say that the vapor exerts when in equilibrium. Just make sure. When in equilibrium with its liquid, I'll move it just now. It's liquid at or within. Let's just move that so you can see it a bit properly. Yeah, let's move that to the side. With its liquid in a closed container. There we go. Oof. Glad I still remember that. So, use the information in the graph above to answer the following questions. What is the effect of an increase in temperature on vapor pressure? Well, Um, the increase of the temperature on vapor pressure would lead the vapor pressure itself to increase, right? Given the fact that they are directly proportional to one another. Remember, the whole concept of boiling point is where the vapor pressure is reached by the atmospheric pressure. And so, therefore, if you increase the temperature, you're getting closer and closer to that vapor pressure, and the vapor pressure would then also have to increase. Um, then they say which compound has a boiling point of approximately 68 degrees. Let's have a look over there. 68 degrees. Okay. Um, well, if you had to analyze this, right, the easiest way to look at it is the fact that the vapor pressure, right, the vapor pressure at which the temperature equals zero would be the boiling point. Yeah. Um, or essentially, if graphically, we're looking for the y-intercept. And by the looks of things, p is definitely not the answer because p is way past 150. R and S look a lot closer to 0 than to 150, so they don't seem to be the answer. Your best bet in this case would be Q. Q is the answer, and the reason why is the y-intercept of Q. Y-intercept of Q is approximately 68. There we go. Okay, and we can fit that one over there. Then, which compound has the longest chain length? Fully explain your answer. Well, I mean, like we said, each time you go down the alphabet, you are adding more carbon. So obviously, then in that case, S would be the last one, and so would be the longest chain length. Now, the explanation for that answer is very simple. We can't really, um, mention the fact that they said to us that each new letter represents the addition of a carbon. But what we can say is the fact that at a given temperature, S has the lowest vapor pressure. Now, if you look at the graph, at any points of vapor pressure, indeed S has the lowest. Sorry, at every given temperature, S has the lowest vapor pressure of each compound. And not only that, but it would have the strongest intermolecular forces, right? Because of that, then given the strongest intermolecular forces, you would need the highest amount of energy to break the bonds within that compound compared to all the others. And those would be your three reasons as to why compound S is your longest chain compound, right? Then they say compound P has 5 carbon atoms. Okay, well that sorts everything out for us. Carbon P would be pentane, carbon R or carbon Q would be hexane, then heptane, and finally octane. Okay, then they say draw the structural formula of a chain isomer of P. Write down the IUPAC name for this isomer. Again, we kind of have, let's see, In this case, we'd have two options as to what we could do. A chain isomer is obviously where you then branch, um, so they have different branches compared to the original chain, but they will still carry the same homologous series name. So they will have different suffixes at the end, um, but you will still be looking at the same homologous series. So I'll just choose one of the possible options, and you are looking at one, two, three. And I'll explain now why I choose this specific type. Three, four, and over here we'll have a chain and hydrogens coming from all sides. There's a specific reason I choose this type. Okay, one, two, three, four, five carbons. And the reason why I choose this type is even though we have a branch over here, look at what I write down for the name. Methyl butane. And I write it down without any um, I write it down without any position number for the branch. Yeah. Um, Position 2 would be the position name of this branch, but I don't write it down. And that is due to a fact of something called redundancy in naming your compound. What do I mean by that? Believe it or not, there's only one actual way to achieve methyl butane, and that would be with the carbon being in position 2. Anything else would give you a different compound altogether. Here's what I mean. If you take the C, right, and you were to move it over here, right, to the carbon next to it, well, guess what? It would still be in position 2, just from the other direction. If you instead moved it to any of these outside carbons, you would now be looking at pentane again. And so because of that, you can only have methyl butane with the branch being in position 2. Okay, then how will the vapor pressure of this isomer compare with that of compound B? Oh, by the way, just to add, the other possible chain isomer of P would have been dimethyl propane. Dimethyl propane. And for the exact same reason, you would not need to include the position of this dimethyl propane branch because of redundancy. Okay, moving on. 3.4.2. They say, how will the vapor pressure of this isomer compare with that of compound B? Choose between higher than, lower than, or equal to. The vapor pressure would be higher than. Why? Because vapor pressure will increase the further away you are from the standard carbon chain. So the more branches you have, the higher your vapor pressure will be, and that's because of differing further and further away from the standard alkane um, carbon chain. Okay, so that will be the end of question 3. Let's have a look at question 4. Organic reactions. This is always my favorite part of the organic chemistry section. Why? Because a lot of the times this is where students tend to struggle the most. Okay, let's just have a look at this. Okay, before even answering the questions, let's just have a look. Let's go ahead and identify what's going on in each case. And hopefully, by doing that, the questions all become simpler. Okay, so let's have a look over here. Okay, compound P looks to be an alcohol. So let's label that. Okay, compound P is an alcohol, and specifically because they have four carbons, it is butanol, and the alcohol is attached to the carbon in position 2. So you have butan 2 all. Butan 2 all. Okay. Just move that closer. Okay, butan 2 all. Then, compound X is an organic product that we don't know much about right now. Compound Y is at least an alkene, we know that much. Compound Z, we don't know much about as well. Okay, they do tell us though that to go from compound P to compound X, a reaction with hydrogen bromide occurs. And so therefore, from there, we can kind of make a bit of movement. So we have an alcohol, and an alcohol reacted with a halogen acid will be a substitution reaction. We started off with a saturated compound. We will end up with another saturated compound, and therefore, in that case, we have a substitution reaction. And because we are about to introduce a halogen, the specific name of this reaction will be halogenation. And the bromine part of this will substitute with, let's just do this. The bromine part of this will be substituted with the hydroxide part of compound P, and what we will end up with is a halogen. We will end up with a halogen compound for compound X. Okay, let's go ahead and name it. Now, in this case, we still would have the foreign substituent being in position 2. It is still, in this case, a butane, but in this case, after the reaction, our organic product would now not be an alcohol, but will be a halogen, a haloalkane. My apologies, slipped my mind for a second there. Okay, and in this case, we end up with position 2, bromobutane, and that would be compound X. Okay, let's just move it closer. That would be compound X. Now, compound Y is as the result, is an alkene as the result of probably what is a elimination reaction, right? And that elimination reaction in itself would cause us to lose the OH entirely. But because a double bond is required, we would also lose a hydrogen. And the specific name of that reaction is dehydration. because in the process of losing OH as well as H, we end up with a complete loss of water. So dehydration, right, to form an alkene, and what we end up forming would be butene, and that butene specifically would be in position 2. Okay, butene in position 2. Let's see. Butene would then react with hydrogen and platinum and would then form, oh, this would be um, dehydrogenate. No, we're adding. My bad. So an addition reaction going from an alkene to a compound Z. We're going from an alkene to an alkane, and this would be hydrogenation, would be the name of it. And what we would end up with is butane. Okay, hydrogenation because we are adding hydrogen. It's in the word hydrogenation. So hydrogenation to go from butene to butane, and okay, that would be E over there. We've already looked at reaction A to form butene, and we said that is dehydration. Well, the opposite of that, reaction B, would be hydration, right? We looked at this reaction going down here, and we said this is halogenation. Well, going back in the other direction would be hydrolysis to introduce a hydroxide. And the one we're left with would be reaction D. For reaction D, start off with compound X, which is a haloalkane, sorry, and we end up with a alkene. Now, to go from a haloalkane to an alkene, we call this process dehydrohalogenation. Dehydrohalogenation because we are losing hydrogen and a halogen. So dehydrohalogenation. Okay. Now we finally can look at what the questions have in store for us. And let's start with 4.1. 4.1, is compound P a primary, secondary, or tertiary alcohol? Give a reason for your answer. Now, the difference between a primary, secondary, or tertiary alcohol is a primary alcohol will only be bonded to one other carbon, right? So if you have a carbon at the end, you would have a primary alcohol because that carbon would only be bonded to one other carbon. A secondary would be bonded to two carbons, two other carbons, and a tertiary carbon would be bonded to three other carbons. So if you look at this case, we are looking at a secondary alcohol, right? Secondary alcohol. And the reason for that is our carbon is bonded to two, let me just add two other carbons within the chain. Okay. And that should make sense, right? If it were bonded to one, it would be, if it were bonded to one, it would then be a primary alcohol. And if it were bonded to three, other carbons, it would be a tertiary alcohol. Okay, then the elimination reaction represented by A. Well, A would be going from an alcohol to an alkene. And like I said, we would lose not only the hydroxide OH, but we would lose an H as well. And OH plus H would form water. And since we would be losing that, the process is called dehydration. Okay, process of dehydration. The addition reaction represented by B, well, that's going in the other direction. We would be adding OH as well as an H, and so we'd be looking at hydration, right? And that is accomplished by adding water to the compound, reacting it with water to form that alcohol. Then the elimination reaction represented by D. Now we said D, you're going from an haloalkane to an alkene, and in this case, we would lose the bromine and we would lose one of the H's as well, and because of that, we call it dehydrohalogenation. Dehydrohalogenation. Okay. Dehydrohalogenation for reaction D. Ooh, 4.3.1, they say sodium hydroxide is used as one of the reactants in reaction C. Let's have a look at reaction C. Without moving the entire thing, let's just reverse that. Sodium hydroxide is used as one of the reactions in reaction C. Okay. Then they say, what type of reaction takes place here? Let's just have a look. I'll tell you what, I'll give you a bit of a minute to have a think for yourself. This is actually a very good question. So they basically say sodium hydroxide will take compound X, which we labeled as 2-bromobutane, to a butane 2-ol, and that is through the addition of sodium hydroxide. Sodium hydroxide being NaOH. Now, they want us to consider a couple of things. One, what type of reaction takes place here? The general name as well as the specific name, and then state the two reaction conditions for this reaction, very specific as well as write the IUPAC name for compound X. I'll tell you what, I shall give you a minute to try to consider it, and I will be back to relay the answer, and you can see if you get it correct or not. I leave this one for a minute just so that I know for sure that you give it a try. It's one of the main challenge questions for organic chemistry and specifically organic reactions. So give it a try, and in a minute or two, we shall dissect it. Okay, so I think that was a bit of enough time. We can now look at it. So, what type of reaction takes place here? Okay, very straightforward. It is a substitution reaction, right? And not only that, it is specifically hydrolysis. It already stated that much. So, hydrolysis as a form of a substitution reaction. State the two reaction conditions that are required. First of all, we need heat, okay? But not only any heat, we need moderate heat. Does not need to be heated that much, but certainly does need to be heated. The other important thing is we need dilute NaOH. Now, you're probably wondering and you're asking yourself, why should we care whether it's dilute or not? And the secret to that is understanding the fact that the difference between dilute NaOH and concentrated NaOH would mean the difference between a substitution reaction or a complete elimination reaction. With dilute NaOH, the compound itself, the sodium hydroxide, does not carry enough moles in it in order to completely facilitate the removal of that hydrogen bromide or hydrogen bromide, and so therefore will settle for, it'll almost settle for a substitution to introduce the OH. But if it is concentrated NaOH, the way I think of it is, at that point, it is carrying enough moles in order to facilitate a complete transfer or a complete stealing of that hydrogen bromide reaction. And in actual fact, what will then happen is you will have a elimination reaction instead, with a different result. So definitely has to be dilute sodium hydroxide and moderate heat. For the elimination reaction, it would have to be concentrated sodium hydroxide as well as a very high heat as your two conditions. Now, write down the IUPAC name of compound X. We've already done that over here. It is a 2-bromobutane. Okay, just put that back there. Cool. That is question 4.3. Then write down the formula of an inorganic reactant required for reaction D. Let's just have a look. Let's not move the entire thing. Reaction D, we go from a bromobutane to butene. Now, in actual fact, exactly what I was explaining just now is what would happen in reaction D. Concentrated NaOH would facilitate the complete transfer and would remove this would remove this Br. Not only that, but would take a hydrogen on along the way with it, and you would end up with an alkene, right? And so the formula of an organic reactant would be NaOH. Had they said as a condition, you would have then had to answer that it would have to be concentrated sodium hydroxide, but they did not. Then they say, using structural formulae, write down a balanced equation for reaction E. Let's have a look at reaction E, and I'll write it over here just so that we can remain in sight of what reaction E actually entails. But we said butene to start off with, right? Write that a bit nicer. And this would be your double bond with H's stemming in all directions. Okay, and that would be in reaction to hydrogen. Hydrogen in this case would look something like this. What you'd have is a result is an alkane. Butane, to be specific, like we had said earlier on. 1, 2, 3, like that, ensuring that all the carbons have indeed 4 bonds between them. And that would be butane. And that would be the answer to 4.5. The next question says, write down the IUPAC name of compound Z. Let's see. Oh, well, there we are. Once again, we've been able to answer a question before they really ask it. The compound Z has a name, butane. Okay, and that would be the end of question 4. Now, let's take a breather. And just as a bit of a summary on organic compounds is 1, you definitely need to know each homologous series type, their general formulas, as well as what they look like, any commonalities, what the isomers entail, what different type of isomers there are. There's position isomers, there's structural or chain isomers, and there are functional isomers. The easiest one is always functional isomers, because you either are looking at an aldehyde and a ketone, or you are looking at an ester and a carboxylic compound. Those are the 2 types of functional isomers, and you get none else at a metric level. The other thing is, for example, knowing that a functional isomer will have a complete different functional group name, whereas a structural isomer will only be a change in the suffix, a change in the name, but not the suffix, as well as a positional isomer will have no change in the name, no change in the suffix, but rather the numbers of the positions. Then from there, knowing how to dissect a question like question 4, where you're looking at a reaction. And the thing to note over there is really the fact that before working on, well, first of all, know the different reaction types, as well as what they form, what the reactants are, and so on and so forth, what the conditions are. Very important to know what the conditions are, as seen that they will ask it in a question like this. But also know to first look at the reactions yourself and try to figure them out before attempting the question. Because most of the time what happens with us is, by the time we get to the question, we are so eager to answer the question that sometimes we will overlook some of the obvious things to note, such as, for example, HBr bonded to compound P would give you a haloalkane and nothing else. Sometimes stuff like that tends to get lost once you start with the question. So have a look at the question before answering and trying to figure out as much as you can. Other than that, good luck with your organic chemistry section. I hope this has helped, and I shall see you in the next video. And in the next video, we will be doing some of the other sections in the question paper 2017. Cheers. Have a great one.